Hi guys, this is your video on rates of change. You're going to take some notes on this. It's going to be a big weekend, so make sure that if you want to look at the quiz early, you can do that. Otherwise, make sure you get your questions down in case we need to work on this next week, okay? So rates of change. Okay, so this graph is showing us a runner's distance by number of hours, okay? So how many miles does he go in 2 hours? So we're going to look at this graph here. And it's going by ones. And in 2 hours, which would be right here, it tells us that he goes 8 miles. What will his speed be per hour then? So if it's going to be miles over hours, that's miles per hour, because division and per are synonymous, we'll take 8 over 2, and that would be 4 miles per hour, which is pretty freaking slow. He's probably walking. But that's okay, I suppose. I prefer to go faster, but that is just me. By the end of this lesson, we're going to talk about these rates of change and how they can look different for lines and graphs that aren't lines. And we're going to talk about direct variation a little bit. So what is a rate of change? A rate of change is how one quantity changes with respect to another. So usually what we use here is we use a delta x over delta I here. I did that backwards. Delta y over delta x. The change in the y over the change in the x. The little Greek symbol delta means change in. A line has what we call as a constant rate of change. That's our first experience with rates of change that we give students. And you know this to be called slope. So because it doesn't matter which points you pick when you're doing a rate of change, the change in y is 8 over 2. That would be 4. It doesn't matter if you pick those 2 points or if you picked these 2 points. This would be 4 over 1. Or if you picked this point here and this point here, which would be 2 over 0.5, because 2 divided by 0.5 would also be 4. Because it's a constant rate of change, we call that the slope of a line. Only lines have slope, but all graphs have rates of change. So that's important for you to write down. Only lines have slope, but all graphs have rates of change. Lines are the only ones that have a constant rate of change, no matter what points you pick. So let's practice with slope or rates of change of these lines, okay? These lines are both called direct variation. These are all, we can use the equation y equals kx. And the reason they're direct variation is because they go through the origin. Both of these lines go through the origin, so the y-intercept is 0. And in this case, k is the same thing as what we usually use as m for the slope. So if a line goes through 0, 0, we call that direct variation, and we use this equation instead of y equals mx, even though it's about the same thing. For some reason, we use k when we're talking about direct variation. So what is the slope? Well, here's a nice point. We look for what we call lattice points. This point's okay, but this point is better because I'm confident where it's at. So we look for the change in y over the change in x. I'm going down 1 to the right 2. So negative 1 over 2. Some of us have used rise over run with slope before, and that's perfect. If you spell rise incorrectly, you could spell it with a y. Why would I ever want to spell rise incorrectly? Because that reminds me that the y's go on top. And the formula that a lot of you have been taught was y2 minus y1 over x2 minus x1. And you probably called it the slope formula before, but you can also call it the rate of change formula. So this is the formula we will use for delta y over delta x. And if you use a line, it doesn't matter what points you pick, it'll reduce to the same number. Here's another practice with slope. The dots are already nicely picked for us. The scale is going by 1, so make sure you pay attention to that. I'm rising 2, and I'm running 3. So my rise is 2, my run is 3, so my slope is 2/3. Remember, the line y equals x is kind of our mother function of lines. That's that standard slope. The slope of 1 is a 45-degree angle if you have a perfect piece of graph paper. Anything less than that Anything less than that would be less than 45 degrees, and anything greater than that would be greater than 45 degrees with respect to the x-axis. So you should be able to kind of think in your mind what these slopes might look like. So we just talked about direct variation, and it's a special type of line that goes through the origin. We use this formula for some reason, and definitely k can't be 0, because if k was 0, it would just be y equals 0, which is not the line we're looking for. We call k the constant of variation, but we also know that k could be called the slope because it tells us how one quantity is changing with respect to the other, the rate of change. So constant of variation, slope, and rate of change are all synonymous with direct variation lines. Let's look at this example. Find the ratio of book price to number of pages for each ordered pair. Round your answer to the nearest hundredths. Are these ratios going to be constant? Well, first of all, it's kind of confusing that they went out of order here, and that will help. That makes things a little tricky when you're looking for a rate of change. It would be more helpful if it was in the right order, first of all, and it would also be more helpful if they took constant steps so that you could see what the relationship it is. But since they did not do that, we're going to have to use some sort of formula to find that change in y over change in x. And our best bet would be to use the y2 minus y1 over x2 minus x1. So we're going to pick 2 points, and they picked, oh, I guess that's not what they're doing. I would have picked 2 points anyway, and we could pick this one and this one. And you could take y2 minus y1, 625 minus 5, over 125 minus 100, and that will give me $1.25 over 25. And if you take 125 divided by 25 in your calculator, you get 0.05 as the rate of change. Now, what they were doing here is they were finding the ratio of just putting the y over the x, so the 5 over the 100. And on this one, we can do the same thing. The 20 divided by 400, because we were supposed to figure out if it was a line or not. If I take the 625 divided by 125, that's also 0.05. And if you take 15 divided by 350, that, oh doggers, oh dogs, look what that is. 15 divided by 350 is 0.04. Okay, so I shouldn't have even used the slope formula, which was kind of risky business of me because this is not a constant rate of change. So it's not a constant rate of change because this guy messes that up. That step is a little bit different. And because of that, it's not direct variation either. Can't be direct variation if it doesn't have a constant rate of change. I do think it would go through the origin. I do think 0 pages would cost $0, but it's not direct variation because you don't have the constant rate of change. Okay, let's look at this. Is this direct variation or not? Based on the graph shown to the right, which is now to the left, whose phone cost varies directly with the amount of time spent? Direct variation looks like a straight line. Both of these look like a straight line, but only one of them goes through the origin, and that would be Nikaya, I think. And that is because Nikaya's passes through the origin. All direct variation has to go through the origin. We might as well practice with some slope here, though, because both of these have slope because they have constant rate of change. But let's figure out what Nikaya's plan. What would the constant of variation be? The constant of variation would be the same as the slope because m and k would be the same thing. And you would have to find the delta y over delta x, the change in y over change in x. You'd be really careful with your scale here because we're going by tens this way and we're going by ones this way. So from this point, let's find another lattice point, a nice even point. Here's a good one right here. So my change in y would be up 30. My change in x would be 2. So the direct variation constant would be 15, and that equation could be modeled by y equals 15x. This guy is not direct variation, but we could still talk about the slope. From 20 to, let's find a nice point for you. Ooh, it's hard to find a nice point, isn't it? Yeah, it's not very nice points. We would have to guess. Let's guess about right here. Okay, that would be a change in y would be 10 from 20 to 30. The change in x would be 1.5. So 10 divided by 1.5 would be, I'm going to hit math 1, 20 over 3 for a slope. And that's probably why it wasn't very nice. Okay, so make sure you try to find nice lattice points if you can. And remember, direct variation has to go through the origin, but some lines do not. So what if it's not a straight line? What if the rate isn't constant? On this graph, it's not a straight line, but this is more accurate for how we would run. We might go fast for a little bit and then slow down. If you look at the endpoints, you could say the average rate of change would be a rise of 12 and a run of 2.5. Well, 12 divided by 2.5 is 4.8 miles per hour. But that's not how fast they went all the time. From this point, the star to here, we went 4 miles in 1/2 hour, which is 0.5. In that time span, this runner was going 8 miles per hour. If you pick any other 2 points, looks like, when do you think we were going the slowest? Maybe like from here to here, or no? I think it going slower maybe from here to here. Okay. In this range, it looks like you went up maybe 1. Let's say you went up 1 and you 1 mile in a 1/2 hour. So 0.5 hours. 1 divided by 0.5 is they're going 2 miles per hour, and they might as well crawl. Okay, so depending on what 2 points is how you would figure out the speed. If they wanted to know the average rate for the whole trip, you could use the endpoints. Otherwise, you'll need to know the intervals they're talking about and find the rate of change, which would be the slope formula between those 2 points. So let's practice some. What is the rate between 0.5 and 2? 0.5 hours is here, 2 hours is here. So you're looking at 0.5, 4, and 2, 10. Delta y over delta x. The change in y would be 10 minus 4. The change in x would be 2 minus 0.5. 10 minus 4 is 6. 2 minus 0.5 is 1.5. So you would take 6 divided by 1.5 in your calculator, and you would get 4 miles per hour. What if you would have picked 1.5 and 2.5? Well, 1.5 is happening right here. It looks like at 7. And 2.5 is at 12. So we'll do the delta y over delta x again. The change in y would be 12 minus 7 over 2.5 minus 1.5. And that would be 5 over 1, or 5 miles per hour. Make sure when you're using your points, you always go from one point to the other, one point to the other. You can't jump and forward, back and forth. So when we compare the rates of change, what can we say? We can say that the runner went faster from 1.5 to 2.5 hours than they did from the 0.5 marker to 2 hours. Okay, using a function to find a rate of change. Here is a function. Do you know how to graph it? Well, you can type it in your graphing calculator if you want. Make sure when you do the square root, you get out of the square root key when you put +1. But this is a square root curve that will be up shifted 1. You can make an XY table if you wanted to do that as well. If you plug in 0, square root of 0 is 0. 0 plus 1 is 1. If you plug in 1, the square root of 1 is 1. 1 plus 1 is 2. I don't want to plug in 2. It's not fun for me. I'm going to plug in 4 next. The square root of 4 is 2. 2 plus 1 is 3. Okay, this is what the graph is going to look like. It's going to be kind of a curve here. And they want to know what the interval for the rate of change would be from 4 to 9. Now, my graph shows what happens at 4, but it does not show what happens at 9. So what we can do is we need to get two ordered pairs. So you will plug in 4 into your equation, which we already did. We got 3. So 4, 3 is a point on the graph. If you plug in 9, the square root of 9 is 3. 3 plus 1 is 4, is another point on the graph. Now you can find the rate of change, which is not the slope because it's not a straight line, and do delta y over delta x, which would be 4 minus 3 over 9 minus 4. And you will get 1 over 5. So the rate of change would be 1/5. Or if you wanted to say 0.2, you could do that as well, because 0.2 could be over 1. Whatever makes more sense for whatever type of problem you're looking at. Okay, what would a negative rate of change mean? Well, it means sadness usually. If you are looking here, when you pick these 2 points, obviously this is a positive growth, but what happens here from 2 to 3? Well, sadness. Like I said, from the beginning to the end, you're looking at positive, but if you're from if you go from 2 to 3, this is a negative rate. So let's see what happens here. So you have 2, 100, and you have 3 that goes with 60. And my little thing is in the way, so you can't quite see what you're talking about. Oh, sad. I just skipped the page. Son of a biscuit. Oh my gosh, something is happening. Okay, well, we're just going to be off the screen for a minute here. Okay, and my stars are in the wrong spot now, so oh my stars. Okay, so let's find the slope and see if we can figure out what that means. Well, if I take 60 minus 100 and 3 minus 2, I get negative 40 over 1. Well, what am I talking about? Well, this is change in y over change in x. So the change in y is sales. The change in x is weeks. So what's happening here is I lose 40 sales per week. So I dropped in sales money per week. So I lost $40, or I sold $40 less in sales that week. So that means sadness in this case. Let's see what this is talking about. Which graph shows a function that always has a negative rate of change? Well, this one has both. This one has positive and has negative if you pick over here. This guy has negative if you pick here, negative if you pick here. And now here, what's happening is it's kind of decreasing really, really slow. So this is the one that always has a negative rate of change. This one has positive rate of changes, positive slope, depending on what points you pick. Okay, let's look at this guy. What is the average rate of change between 1 and 2? So here's 1 and here's 2. Let's figure out what that slope would be between those 2 points, or the rate of change formula. So what would I be doing? I'm counting by 2s here. So this point is 1, 2, and this point is 2, 4. So my change in y would be 4 minus 2 over 2 minus 1. So the rate of change here would be 2. Between 2 and 3, well, at 3, the point is going up to 8. So I would do my change in y over my change in x again. And I would have 8 minus 4 over 3 minus 2, 4 over 1. The rate of change here is 4, which is greater, and you can see that the slope would be greater. How about between 3 and 4? That would be 3, 8, and then 4 is going up to 16. So I take 16 minus 8 over 4 minus 3, and the rate of change would 8. And for this function, as x increases, the rate of change also increases. It gets steeper. And this looks like our last problem. And I just didn't delete it from my last homework. So I think that's it, because this is not even supposed to be there. Okay, so that's it. There was a little distraction. Mrs. Chen came in and bothered me. So I hope you take good notes, and you can take a look at that quiz, or you could wait until I see you next week.